Well, thank you for that introduction. And in advance, I want to say that I want to acknowledge the many people who have inspired and collaborated with me throughout this time that I'm going to be covering. Most especially my dear friend and collaborator, Alan Kay. So in 1971, I found myself working on a project at Xerox PARC, helping George White to set up a sort of a workbench for studying speech recognition. And that was a lot of fun. But I kept, when I was in my office, actually we worked down in the basement, but when I was in my office, I kept being more interested in conversations I heard across the hall where Alan Kay had just moved in. And I had been looking at, I had been doing a bunch with Fortran. I started computers really late in college because computer science didn't exist as a study and Harvard didn't have a computer science course. But while I was working on that project, I got interested in a system called Meta 2. Who here has read about Meta? Okay. So that's, I'm experiencing that percentage because it was published in 1962. And I want you to know that some of the things from back that far are just gold. So I highly recommend that to you. It's written by Val Shorey, and you can curl up with it some night, and in 5 pages you'll be amazed that he can compile Algol and then actually compile the compiler itself. And it's all understandable. Anyway, I'd been interested in maybe doing some sort of extensible language from that. And Alan knew much more about extensible languages than I did. He always knew much more about whatever it was than I did. He read widely and understood deeply. Anyway, he was clear that in extensible languages, you have the problem of creating more types, and then there's a sort of an n-squared problem of complexity. And he, from his other experience, working at the AI project and other places, had seen that the way to get around that problem is to make sure that all the interactions are simply message sending rather than direct links. And we were talking about this in a conversation. I think Taylor was there, and Alan said, you know, I bet in less than a page of code I could write a language that would be object-oriented and operate by sending messages. And we said, oh yeah, show us. And he did. And that became Smalltalk 72. And so what about Smalltalk 72? It is true in that system, everything is an object. And computing happens by sending messages. What? You mean 3 plus 4? Yes. And that was so unthinkable at that time. You know, how can you actually compute that way? Each object is an instance of a class, and there was no syntax as such. This was really strange, but the way it worked was that when you referred to an object in an expression, the object got the rest of the expression as a message stream, and it could then pick through the message. So you sort of got the syntax happening localized by each object. So anyway, I wrote, from Alan's description, I wrote a proof of concept in BASIC. That was because I was trying to work from home. We had just had a child. And when I could see it would work, I wrote a serious interpreter in Nova assembly language, the language of the alto. Much better. So the alto was a beautiful machine designed by Chuck Thacker and Ed McWright and Butler Lampson at Xerox PARC. And it featured a high-resolution bitmap display. And for things at that time, it was almost unimaginably beautiful. And the goal for it was to be able to display one page of beautiful text, because Xerox PARC was created to explore the office of the future. And sure they figured that people wanted to look at beautiful and clear documents. It did not have much memory. It had 64,000 16-bit words, very short there. But it had a microcoded processor running at 5 MIPS. And of course, that got reduced to only 1 MIP because that was microcode and the memory cycle time was a microsecond. And that got further reduced to a half a MIP because the microcode had to spend half of its time running around and actually refreshing the bits on the screen. So, but we did what we could with it. And so our project piggybacked on the sort of Office of the Future effort. And we had access to those machines as soon as they were able to run. And we almost lost the Smalltalk 72 artifact, except that when we left Xerox PARC many years later, a few of those disk packs were saved. And I got hold of one of them, a couple of them, that actually had a binary version of Smalltalk 72. And I thought, ooh, wouldn't it be cool to revive that? And at that time, I was working in the lively kernel, which is JavaScript, and I thought this would be a fun thing to do in JavaScript. So I set about to do that. So there's a picture of a debugger screen written in JavaScript looking at this binary image I picked up. And if you look at it, it's frozen at this point right after it called outload, which is where the system would call itself and write itself on disk. So this is where it got saved 40 years or so ago. And you can actually pick it up. So you can see the accumulators simulated down here, and you can step through the program like that, and you can run it at a reasonable speed, or you can just run it at full speed and show the display, and boom, there it is, writing the welcome banner. And what we would always do when we started it up is, as you might guess, write 3 + 4, and it comes back 7. That means that at least half of the system works. It had to, that's running the interpreter, running the read routine, all that good stuff. And then I would always do, that ran the floating point system and floating point printing, which was far and away the most complicated code in Smalltalk 72. Most people didn't look at it. And then you could start to have fun with things like this. So this is a for loop, and it's saying, okay, so I need to explain about the that little smiling thing. That was Smiley, our resident turtle, which was programmed according to Seymour Papert's turtle geometry. And you could type it with a single character, which made it easy for kids to do. I'll just... Now, I don't know about you, but something inside of me goes, yeah, when something like that happens. And one of the points I wanted to make here is that through all of our systems, and Alan inspired this also, we try to take the fact that we're working with an active machine. If there's anything about it, it's live. It's trying to do millions of things for us. And we've always tried to sort of preserve that liveness in the systems we've built, and the graphics we've built, and the UI. So that's just a quick demo. Let me show you, I'll just speak briefly about this code, because I think I already said a few things about it. Essentially, this is, there's the statement I typed in for I to 300, smiley go I turn 89. I actually didn't write do there, so we'll get to that. The way the system works is it looks up for and starts running the associated method for it. And I'm just going to read through this without explaining it all. It first says fetch the next thing quoted and store it as var. So that's the atom I. And then look for a left arrow, and if you see it, then store the starting value. You don't see it, so store 1. Look for the token 2, and yes, we see it, and so store into So fetch the value of the stop. In this case, it's 300, but it could have been an expression, and it would have gone through and parsed that. Store it as the top. Look for the token by. Don't see that, so just set the step to be 1. Look for the token do, and don't do anything. So that's a buzzword. So it allows you to write syntax that might be a bit more descriptive or helpful, but without doing anything about it. And then fetch the next expression as a literal array. And then down here, so then Smiley starts running as a turtle. And this code down here, I won't go deeply into it, but that's the code for what a turtle does. And you can see it's laid out here. We very quickly realized the sort of style of writing an object-oriented class. So there's a method here for goTo, a method for go, for turn, for pen, and so on. And go, I'll just fetches the distance, and then says self goTo, my current position plus, and this creates an inline point whose x-coordinate is my direction's cosine, and y-coordinate is my direction's sine, and then takes all that. So now we've got an array. So even in Smalltalk 72, we were able to have these sort of nice graphical algebra of points and rectangles. So that array times the distance. And then it returns itself actively, and that allows Smiley to continue on and see the message turn. So there you have it. Really simple. So Smalltalk 72, its upside was it was easy. Look at that. It says easy to teach, and there's a Dahl. So there were some things difficult to teach about it, but at least it wasn't a lot for kids to type, and we could explain, well, just do this like that, and so on. Objects and messages really worked. So this system ran slow as molasses, but it was really simple, and it actually worked. And it was great to get experience with classes and instances and a message sending protocol for everything. And we never had to wait for completion. And this is the great thing about sending messages. I don't need to preach it to this crowd. But the two things are, because there are no direct pointers for invocation, you never have to recompile the system when you make a change. And moreover, you don't have to stop your work and reload all of that when you make a change. The downside, as I said, it was slow as molasses. It was already a slow interpreter, but now get it to parse everything it does every time. The other one is you can't read it. So when you read a piece of that code, you'll get something, and there will be another token, and you don't know if that goes with the thing you were reading or if it's going to be part of something else. And that's a real problem. If you wrote the code, it may not be too bad a problem, except if you look at it a couple of months later, it may be. But even worse, I think worse, the compiler's in the same position. It can't read it, so it can't compile it. And at that time, I really wanted to get stuff. We all wanted to get stuff to run faster. Also, it lacked inheritance. And we already were finding stuff we wanted to be common between integers and floating points, and also between character strings and arrays. So that was something else. But it was a great proof of concept in that sense. So Smalltalk 76. We wrestled for a while with how to compile this stuff. And then I sort of had this flash about how to do keyword syntax, because a lot of the things in Smalltalk 72, we had a bunch of keywords on the line, and we were all kind of resistant to go into a highly parenthesized language, such as C or Lisp. So it kind of solved that problem. It worked out nicely. And then it needed a stack machine to interpret it. And everything was done by messages and inheritance. And so let me, So there's a simple diagram of the system. And the upper part is the static structure that you all know well, with classes and method dictionaries and compiled methods, sort of in the middle. And then the bottom part includes the contexts that have pointers into the progress in methods, and also the temporary storage for temporary variables and stuff like that. To get this going, we actually wrote a simulation in Smalltalk 74. The Smalltalk 74 was almost indistinguishable from Smalltalk 72, except we tried to move in some of these directions, and there was more about how to take apart message streams. But the cool thing about this, the simulation we did had all of the classes describing this structure running as Smalltalk 74 sort of generating classes, but also the actual objects themselves. So when we got it running, everything ran okay in this context, but we still had contexts in there as real objects. And that was kind of revolutionary. We didn't realize how amazing that was. And you know, this sort of comes back to using your system live, the benefit you can get out of that. So, so this gave a bridge between the interpreter state and the user state. So all of a sudden you could write the debugger in the source language. And that was sort of unheard of then. I mean, debugger is something written in assembly code down below, you know. And in fact, even beyond that, you could even put an interface to it out in the user interface. And that was sort of unheard of. So that was pretty cool. And I want to give you a little demo of that, but I wanted to say something about the compilation, which is, yes, it was compiled, but the aspect of compilation was to get the syntax out, to parse it through once, and compile it to bytecodes. But the bytecodes were not what typically got compiled in systems of that time, which would be direct calls through linkages to primitive procedures. Instead, it compiled to messages. So in this example, for the method max, we have self less than other, then return the other, otherwise return self. This is Smalltalk 76, but you'll get it. And this compiles into 10 count of 10 bytes. It's very compact. So push the argument, push yourself, and then send less than. So that's a send instruction. It's not a call. And that meant that this code was generic code. So it would work for anything that was a subclass of that class. So in particular, in the number hierarchy, it would work for integers and floats. And if you added a class fraction, whoop, all of a sudden it understood how to do max without having to add any code. And that's because it also had inheritance. So that was pretty neat. And if you think about it, you could even go to the extreme of passing in a type. So the argument, these self and other could actually be types, like type integer. And it would do a less than. And what does a type, what would type integer and type float do about less than? Well, probably return number type. So you can have fun there with type inference too. But that's just to say that the compilation into abstract message code is very flexible. So let me just show you a little bit what it's like, what it was like to run that system and what we showed people in the world. So one of the things we would show people, and especially people in the community of thinking about the office of the future, is we would do experiments with people who were not used to computers but just using them in offices. And they would take our nice text editors, but they would make big selections like this. And what they actually expressed was that it was scary to have this big black hole in the middle of the screen. And you can imagine that. Remember, people, they're just used to working with paper. So I would have somebody beside me and say, you know, well, how could we fix this? It'd be nice if we could instead do an, you know, outline that. And what tools do we have to work with that? And so I'd come down to this little workspace and write something like, so a first thing that I would say is, well, you can get at the system, everything happening in the system, just right at the top. Let's say this. Oops. Oh, I know what I did. Yeah, sorry about that. So I could, it sends the message from user to rectangle. It asks me to show it one, and I do like that. And it prints back what it got. And this was already unusual, in the middle of just typing text, to be able to get at the system and evaluate stuff. And so let's try something a little more interesting, which is to Now, if I select that rectangle, it's going to do this operation called comp, which is to turn it black on white. Okay, so we can have fun and do that a couple of times. And it's you know, to people who aren't used to that, it's really kind of amazing to see. Gosh, I'm actually in the system now doing something a little bit programmatic. Let's do another couple over here. Realize that if you, in the process of this, we might get a couple of rectangles that are just offset one from the other and realize, oh, that's an easy way to do, put an outline around something. Maybe we could use that to change the text selection. So now we go up here to say, well, let's see, where does it do selecting text? And we go to this, the text image class, and we look at the category selecting, and we see this method complement from one thing to another. I think it's from the beginning to the end of the selection. And here it goes through a bunch of computation, and then down here it's, so one of the things about a selection is it's got a top partial line, and then a big black, that's the big black hole of complete rectangle, and then a bottom partial line. And you see that code here. There's the complementing for the top partial line, and then the middle block. And each of these calls comprect. So let's see what comprect does. This is already astounding to people because all of the source code is online, and I'm just browsing through it. So let's see what comprect does. And here it says, okay, to comprect a rectangle, intersect it with the frame, intersect it with the window, and send a message comp to it. And that's what we were doing, right? Is that comp. So let's take this and copy it. Paste it. And you mean we're actually working on the system code? That's right. And instead of R here, let's do R copy, translate by 1 @1. So that's a way of doing an inline literal point. Just sends the message @ to make a point. And let's, so now we've got a new method that should do that. Let's compile it. And let's make a selection. Oh my gosh, look at that. It's kind of skinny, so let's go back and make these maybe 2. Okay, and then we can go look at some big method. Look, Ma, no black hole. So that was, as I say, it was extraordinary to people at that time. It's people in industry, and not only that everything was online, but here I had gone and actually changed the system method and didn't quite like it, changed it again, and how long did it take? No time. And so it was clear that not only was this a flexible way to design stuff, but for exploratory development, you've got somebody there who's trying to deal with some customers, and he says they don't like this, fix it. I'm going to talk just briefly about BitBlit. So as wonderful as the Alto was, it meant that from the beginning we had to deal with this problem of representing images in a linear memory broken up into words, and how big words, 16 bits, 32 bits, 8 bits. So to actually move an image from one place to another, or to combine two images on the screen, was a mess. You had to do all this shifting and masking at the left side, shifting and masking on the right side, and you had to do that for the source and the destination. And we had in the Smalltalk code at that time, lots of cases of this, for drawing lines on the screen, for putting characters on the screen, for scrolling stuff, for moving stuff. And I wanted to clean that up, and so I worked on this for a long time, and started to get pieces of it. And the one thing that was bothering me was the need to keep doing this masking as you go, as shifting and masking as you move across the line, and also had to do the whole thing without temporary storage, because that was a problem too if you wanted to do a big one. And one night, my kids were playing with these rubber stamps, and they had this cool rubber stamp. You ever seen one of those? It's round, and you put it on the stamp pad, and you go, and you can make like a Greek frieze across that way. And that picture suggested this image to me, which is that you sort of got the source going across there, and it's rubbing off on this round thing, the wheel, and then it deposits in the bottom, which is the destination. And I wrote the word boundaries wrong there in that picture, but you get the idea. And the cool thing is that if you make that wheel just be two words, whatever the word size is, then you essentially only have to, once you've handled the masking, the shifting at the ends, that thing can just roll around with one shift each time. So I got that to run on the Alto in microcode, essentially at the memory speed. So in microcode, you can hide instructions like for masking and stuff under the memory access time. So that was a huge simplification. And I wonder how much of this to show you. I'll just go quickly through the next little part. So you could do lots of stuff. Here's an indication of, here's where you use a little rectangle to take out slices of that 7 and then smear them downwards so you can magnify things easily that way. There's this incredibly complicated recursive way of doing a rotation by 90 degrees. But you want to end up, you very soon want to be able to do all these kinds of things. And let's see. So I think I'll stop at that point. We will return to BitBlit in more detail in a little bit. But that was a great simplification and a case of trying to, along with keeping things live, it's really great if you can recognize some simple kernel that is also general, because all sorts of stuff happens that you didn't maybe anticipate. So as an example here, this wasn't just good for the things I mentioned. It also gave you paintbrushes, and it gave you the ability to grab a piece of the screen, hide it, and put up a menu and restore it. So we did pop-up menus when people didn't have pop-up menus, and things like that. animation too. You can move stuff across the screen as though, as though it were in a separate layer. Let's see. Let me just say, so from that demo that you saw, as I say, we had a lot of commercial interest, and Adele was particularly attuned to this in the group and said, and plus we all wanted to get Smalltalk out into the world. And if you look at the images of the Smalltalk balloon, you'll see that it's actually leaving an island. And the allusion is to the island of Xerox PARC. And the best way to do that would be to make it some sort of a standard. And Adele sort of organized the group to get stuff documented and to fix a few things. And I got charged with fixing, making Booleans to look like regular ifs, or certainly not like what we had, and to get rid of those weird characters. So for the most part, we did that. Oh, and she had encountered a lot of need for meta classes and teaching about it, and to avoid having uninitialized instances and things like that. I thought I'd just mention the one thing that was particularly fun for me, which was in making a class Boolean. It seemed, at first when I looked at it, okay, so Booleans will want to do something like, if true, do this, if false, do that. But then, if you write the code for it, it's just going to say, am I true, do this, am I false, do that, which would just be recursive. So you'd have to make it into a primitive. So I sat with that for a little bit, and all of a sudden I realized that if instead Boolean was the superclass, and there were two concrete classes below, which are true or truth and false or falsehood, then they could respond differently to the incoming message, and all of a sudden there's no circularity. And I thought that was so brilliant because I didn't know of any languages in which if didn't wind up with something recursive and primitive. So that was neat. It was sort of an aha, once again, about the value of organizing things by messages, because messaging subsumes this kind of conditional even better than we thought. Let's see. So after the release of Smalltalk 80, I went to Apple and spent a while making Smalltalk available to the world through the Apple Programmers and Developers Association in such a way that it had no licensing restrictions. And then I got called to do a family business in Virginia for the next 8 or 9 years, and sort of left the industry. When I came back, it was 1995, and Alan Kay was at Apple and wanting to do another run at educational software. And as usual, he wanted to have a system where we'd have control over everything. And that to me always seemed like, well, Smalltalk's a good way to do that. But the Apple Smalltalk system at that time consisted of about 100 pages of 68,000 assembly code. So that didn't look very attractive. But in the back of my mind, I realized that since I had left the industry and come back, it didn't seem like much had changed, except all the machines were 10 times faster and much bigger. So this really struck me all of a sudden. I remember exactly where I was in the car in the rain. And I thought, wait a minute, we could actually take the reference interpreter that was written out in the Blue Book, which we all published, and run it. It would run fast enough. I had played around with simulation, so it's really hard to do something when something's in simulation mode, but you can do it. And so that was the scheme for Squeak, and the allusion to the red slippers that I'm sure you realize is from Wizard of Oz and realizing, oh, we had this all the time. So start with the apta Smalltalk 80 as a library, and just run the reference interpreter. So we could get that going, and there was a bunch that had to be done inside the apta code to clean stuff up. But then also start a project to write a translator from that reference interpreter into C, because we needed something that was, for a commercial implementation. That part would have to run fast. And writing a translator was going to be not that hard. For regular Smalltalk, it would be nearly impossible because it's full of message sending, right? But the reference interpreter was written on purpose just to sort of be a macro description of what a virtual machine should do. So it did not use message sending. It used that syntax and stuff so you could debug it and all. So this was an incredible boost, and we even got a freebie from Mario Walshko had taught a Smalltalk class, and they had actually typed in from the Blue Book the whole reference interpreter. So we got that without having to type it in. So we actually got this whole thing running in about the first bits on the screen in 2 months, and the thing really running translated into C in 4 months with these 4 guys. Alan always liked to make the comparison between a small team and hordes in industry. But anyway, it's actually easier to do it with a small team. And this was another one of these experiences, as I described, going from Smalltalk 74, simulating Smalltalk 76. This was the same thing. We were simulating a Smalltalk, and the minute it ran, it was like it was beautiful. It was like a commercial Smalltalk, and all of sort of our code that we liked, and the interpreter itself, malleable. You could debug it in the Smalltalk debugger, and you could write. And previously, it had been really hard to write primitives, and they would be non-portable. But now the primitives could actually be in this what we call slang, non-message sending Smalltalk. So it became much easier to work on hard code, and that enabled us to write a really nice scavenging garbage collector, and I spent a bunch of other things like that. It gave me a chance to go back to BitBlit, and I'll show you just briefly about that. How are we doing on the overall time? That can't be true. Yeah, no, okay. Well, I'll close it up pretty soon. In fact, I'll go very quickly through this. This is just the fact that if you can write an extension to BitBlit where the down at the bottom we're going to a single destination rectangle. But if you write some sort of clever code that's a little bit like turtle geometry, running along, tracing out lines in an arbitrary quadrilateral. I showed all rectangles there, but any quadrilateral will work. It can do rotations and scaling and all that cool stuff. So let's just dive into that. Okay, there's Squeak, and what I'd like to do is first go to jump to project fun with Morphic. So I should say a word before I get into this. Very soon after we got Squeak running, we implemented a graphics model called Morphic, which John Maloney and David Ungar and Randy Smith had worked on. It's a really nice graphics model and nice user interface model. So this is BitBlit and WarpBlit at work, and that circle there is magnifying wherever I am on the screen, so you can go and examine stuff. And this thing over here, there's some outline text done by Andreas Raab, and you can actually move the magnifying glass over. You can see that it's translucent too. And that thing that says live in Morphic is a stencil that's looking through there at a background morph that happens to be just stripes, but it could have been, cowboys chasing one another. And throughout this and everything, we tried to maintain that aliveness. So, you know, is that just text? I can edit in it, and it's still, the stencil tracks that and everything. And meanwhile, I got the basic text working, but Alan was thinking we ought to be able to do documents, you know, we want to be able to publish this stuff in an attractive way. So he said, can you do linkages between frames of text? I said, yeah, I thought it'd be pretty easy. And then he also wanted to be able to do non-rectangular containers. I said, well, so I'll work on that. Worked on that. And then I couldn't resist doing this one other thing. So here's a demo that I gave to Alan when this stuff was working, which is, here's a rounded polygon. And you can see it lays out in time. And it's connected by this little pipe thing to this other text down here. Okay? So this is stuff I just wouldn't have considered doing if it weren't really easy. And so once again, you know, the simpler you can make stuff, the faster it'll probably run, and the faster your productivity will be too. So let me, I'll show you what. This is the thing that we wanted to be able to do is, you know, multi-column text. And I'll just play sound. Now you can see that flowing over into the next column. And the same thing, it does the same thing for the next page. And there's Bitblit doing a little animated page switch. And the test for it was, so the other thing that Alan threw in, by the way, it'd also be nice if you could do runarounds. So if you take this and drop it in the middle of the text, it does runarounds. And let me do this. There's a little control here that lets me drag this without picking it up. So I think that's pretty neat. And so while I'm here, let me just take a minute and tell you about eToys, and then we can take questions. We can get started for a while. So with any of the objects in the morphic environment, we could ask for a little control panel, and there's the one for this ellipse. And it was really neat because I could pick this ellipse up and move it around, and if you look over there, you'll see its ellipse's X property moving and its Y property moving. And I think it was just, you know, a revolutionary bit of education to sort of allow you to see the right and left brain aspects of the scene together. And that meant that, you know, then you had a sense of when the ellipse wasn't visible, if it went underneath something, you'd know that the numbers were there changing, and that's sort of a fundamental thing in how you think about the world. So you could also then, let's just do this. You could do cool things like, I could take this command, ellipse forward, and drop it out in the world, and get a little scripter object, which is a sort of a fancier control over it. And I could push on the exclamation point, and it would keep executing that command. And I could bring this other one, so that was forward. I'll bring another one over here, turn. This is kind of familiar from turtle geometry-like stuff, too. So now it's going to do a forward by 5 and a turn by 5 each time I hit that. And I can just lean on it like that. And I can also set it to, that's in the normal phase. I could also set it to ticking. And that way it just keeps doing it without me having to keep clicking on it and stuff. And you know, if you build everything in a general way, and it's just messages that everybody understands, you can do stuff that you didn't anticipate, right? And so it's a more creative environment if stuff that you didn't anticipate is just possible anytime. It's like Maria Montessori with a bunch of things on the table that you might think of combining this way or that. Okay. Let's see. So I think at this point I'm close enough to the end. I think I'd just like to show one more thing, and which is my favorite e-toy that I ever saw. And it was designed by Alan and involved work from everybody in the group. Let's just get So here's the scene. On the bottom left, you have a MIDI control panel. Oh, do we have, there used to be speakers. Do we have audio here? That's important. We're not for sure. Well, at the very worst, we can turn my poor little Mac up as loud as it will go. So, MIDI control panel, MIDI player panel with that, and up above the scene with musicians. And it's done with, there's a cool thing about the musicians. One is that they're, if you move them up and down, they get bigger or smaller. Is possible? We need to plug something in here. Really? I like that. Yeah. So I'll just keep talking about this. And if you look at these controls down here, you'll see there's a relatively complicated e-toy script here. But if we take the clarinet bear, and his scaler is set to the clarinett's range times a factor. So his size is being scaled by a factor times his y-coordinate, essentially. And so that takes care of this neat sort of three-dimensional effect. And then not only that, but, oh, okay, that's a good idea. Yep. Oh, yes. And then, yeah, okay. And then there's another script there, which I'm not showing right now, which is that the, as you move the clarinet right and left, I'm going to collapse the control panel so you can see it. It's just, see, in this MIDI control panel, there's loudness and pan. And so if I move the clarinet bear closer, it gets louder. See that? That's the green slider. And if I move them left and right, that works. And then the all of the stuff with MIDI, John Maloney worked on that. I worked on this scroller, and let's just fire it off. See if that's, so we'll come up here and say play. That's not doing it. So I can do this. See what you getting that? And now we'll take the clarinet. Oh, you won't get the stereo zoom because we've just got the one microphone. Quiet. Loud. And the same thing, there's the trombone. There's actually more live in there that I didn't pull out, but you can pull out the timbre editor for the each of these voices and change the sounds of the instruments while it's going. Not something you'd likely do, but it made a good show. So, any questions from people? Yes?
Given the changes in speed from the alto to now, do you think it's worthwhile to revisit the approach of Smalltalk 72, like an auditory meta, in sort of a live system?
So I've spent some time thinking about that in a slightly different way, but it is the thing that I got interested in is sort of, again, an historical thing, which is that there's enough speed there, and I actually have a Smalltalk 72 emulation that runs 500 times faster than the alto. And my experience is with most emulations, if you do them carefully, you only lose about 20 to 30 factors. So I thought for sure we could run Smalltalk 72 evaluating itself and have it be usable. But we never did a self-evaluation. So Alan made a spec of the interpreter, and I wrote something that worked, but we never truly evaluated it in the language. And I thought it'd be really nice to go back and do that. So that's something you could do. But with regards to Smalltalk 72 and, would it be worth, actually going with that? It's still got the problems. It's unreadable. It's uncompilable. So I don't think so. And I bet Adele, who taught it to kids, would agree. So it's very cute. It was a wonderful place to start, and it was we really did learn from it because there was a bunch of us in the group who were hackers, and we tried to do everything we could with it, and from that learned how we wanted the next system to be. But I think the answer is no.
To be clear, the kids who learn Smalltalk 72, there weren't a lot, within the schools. Every one of them is in the computer industry today. If they weren't turned off, they were turned on. But we really had to hide things. And we didn't believe in hiding. So there are things you saw that if they saw might have scared them.
So do you feel like Smalltalk 76 and 78 maybe are easier for kids to learn? Or
yes, but we're still not there.
Yeah.
Not a question, but a feedback on Bitlit. I once had the opportunity to teach Smalltalk 80 to some visiting high school students that came to our university. And so I got them doing some exercises. And one of the girls in the class went into a workspace and she typed form, black, white, and ran it. And called me over saying, something's wrong, I don't know what's going on. I don't know if you can tell what's going on just yet, but form black was the standard black color. And white said, paint it white. So now you have a white menu with white text on a white background with a white cursor. And I couldn't figure out how to get out of that mode.
Yeah.
So,
Yeah.
The other feedback is I know somebody who wanted to do massive amounts of integer calculations, and they use Bitlit with, for an 8-bit number, they use 8 planes of Bitlit, and then do ands and ors and exclusive words on the different layers to do the calculations, and then the vertical bits were the answer.
Yep. So you're looking at one of those people. One of the first things I did when I started, actually it came from something I was trying to do for count bits, find out how many pixels are on. So I did the game of life that way, which needs 3 planes.
Yes.
And this was in Smalltalk 74, which still ran like molasses, but it could call bitlit. And the bitlit was running in microcode. So I had this incredibly slow system that was running a 1,000,000 pixel life. Yes, yes, yeah. But there's something I wanted to show here. It's not.
Oh, and when I left that, when I finished that course, at the end of the course, girl who had that problem left a note on my door saying, "Thanks for the course, that was radical." You can tell it was 80s.
Yes, yep. I'll just show you the unit test for workflow. It's kind of fun. So this is copying a rectangle onto itself, scaled and rotated so the mouse left and right is the rotation, up and down is the scaling. And then at every iteration, it also cycles through a color map. And this is really fun to play with.
Oh, yeah.
Yeah. And so we'd fire up the music synthesis. And, that kind of stuff. And then it does near 0, it gets really nuts. And below 0, it's actually scaling up. And so what it does is it's sort of an amplifier of the noise in the name of it. So, other questions? I think we're over time, so I should let you guys go to the next thing.
I feel like Wayne and Garth. I want to go, we're not worthy.
Oh, you are worthy. This stuff, it's not that hard. So I must acknowledge, certainly Xerox and some of the other institutions for having supported us. Making this kind of progress, it requires being able to go around, I think of it as the circle of the scientific method, which is you make an observation, which is like what it's hard to do in the world. And from that, you make a theory, which I'll bend it a little bit, which is what would fix that. And then you make a prediction. You actually do it and see if that fixes it and makes it better. And we went around that circle several times on Xerox's dollar, and of course produced value. But that's hard to do these days. These days you get in a startup with a good idea, and you just try to sell it, and the big companies just try and buy it. But they don't get that same kind of longitudinal commitment.
I don't see too many Xerox parks around anymore, do you?
Yeah, not really. Not really. Every once in a while, you'll find a group inside of, IBM or Xerox or some big company. And I don't know about today's big companies. I don't know. There's one bank. I forgot which one it is. It's continued to support their Smalltalk folks.